Hello, so today we're going to go over a brief review of Chapter 18, aryl halides, vanillic halides, and phenols. So before we get into the reactions, let's be clear on what our base molecules are. So we are working with vanillic halides and aryl halides. Vanillic halides have a double bond with a halide attached to one of the alkene carbons. So it's not directly on that carbon, it's coming off of it. Aryl halides are benzene rings with halides attached to one of the carbons of the ring. We will also touch on phenols, which are like aryl halides, but instead of a halide on the ring, so where that X is, we're going to be attaching an OH hydroxyl group. We have some limitations with vanillic and aryl halides that we need to go over first. It's important to know that both of these molecules cannot undergo SN2 type reactions or bimolecular nucleophilic substitution. Let's look at why. So the top reaction there is attempting to show SN2 with an aryl halide. So as you would expect, we have a leaving group and a nucleophile that will come in and take its place. However, this reaction cannot happen. As we know, the double bonds in benzene rings are constantly moving around. A nucleophilic substitution would end up causing double bonds to twist, and the ring would become disfigured, so that reaction can't happen. Below it, we have a vanillic halide, and so again, the halide is a leaving group, and the nucleophile is substituting in. But the problem with this reaction is that we start off with an sp2 carbon, then go to an sp carbon in that transition state when the nucleophile attaches. This is energetically unfavorable because sp is super high energy, and going from sp2 to sp, it's just too much energy that's required to make that happen. Again, so the reaction cannot happen. Just as SN2 did not work, SN1 does not work either. In SN1, you need to form a carbocation intermediate. So in the first step, we are removing the leaving group, which is a halide as expected, and forming a carbocation. Here, we are once again going from an sp2 to sp hybridization. This sp cation is not stable, and so vanillic halides will not really form at all. This same thing goes for aryl halides. I just didn't show it because it's the same as in this reaction with the formation of an unstable carbocation where that leaving group was removed. So what can these molecules do then? Vanillic halides can undergo beta elimination, which we will talk about a little bit more later in the context of metals. Here we have a dihalide or two halides, and we're removing or eliminating them from this molecule. To compensate for the change in charge, the beta hydrogens are being removed, and those bonds and electrons are going towards the formation of a CC triple bond or an alkyne. This reaction works because of the presence of those beta hydrogens. We can't do SN1 or SN2 type substitution, but we can do nucleophilic aromatic substitution. So here a nucleophile, in this case OCH3, is attacking the carbon where our halide is attached. At the same time, we're going to be moving around those double bonds to adjust for the nucleophilic addition. What ends up happening is a transition state called the Meitner complex is formed, which has many resonance structures. The only difference in these structures is the placement of those non-bonded electrons in the double bonds. Again, it's resonance. But what ends up happening is the fluorine will leave, and the non-bonded electrons will be pushed towards the carbon where it attaches to balance the charges. We can see our products there on the bottom, and to summarize here, we were able to substitute a halogen for our nucleophile OCH3. Let's look at some of our fundamental reactions as Chapter 18 in the textbook decides to call them. Knowing these are really important. It's really important to know all these because they are going to show up in more complex reactions we do. These reactions will involve transition metals, which are in the D block of the periodic table. So just like we have the octet rule for atoms outside the D block, we have the 18 and 16 electron rules for our transition metals. Transition metals have a filled electron shell when they reach 18 electrons, so that's in its most stable state. 16 outer shell electrons is also a stable electron configuration, hence the 16 electron rule. For more information on this, I recommend referencing page 894 in the textbook, which goes into more detail on these rules than I'm going to go into. Okay, so let's get into our first reaction, ligand dissociation association. All we are doing here is removing a ligand, PPH3, that is bound to palladium. So it's simply leaving the metal, taking its electrons with it. This means it can go from 18 electrons to 16 electrons, both of which we know are stable based on those rules. The ligand can also reassociate or reattach to the metal, so it's kind of two-way here, hence why it's called ligand dissociation association. Oh my goodness. Our next one is ligand substitution. Here, one ligand is dissociating and a new ligand is associating to the metal. In this example, iodine is the ligand that is dissociating and CH3 is the ligand associated to take its place. The number of electrons are constant here, as we see it going from 16 electrons to 16 electrons. In these types of reactions, it's most common to see X-type ligands dissociating and an X-type ligand associating, or an L-type ligand dissociating, then an L-type ligand associating. So what do I mean by X and L? Well, to put it simply, our X ligands are kind of neutral and our L ligands are charged. So as long as we are doing X for X and L for L, the number of electrons overall should not change. Our next reaction is oxidative addition. Here, a metal is going to insert itself between two other molecules that were previously bound to each other. So that original bond is going to break, say between the R group and the bromine in that first example, and the atoms will form a new bond with magnesium, our metal. This will cause the overall number of electrons to change, which is what we are seeing in that second example, which I have the number of electrons labeled there. In the second example, the bond is breaking between the phenol and the iodine, and they will form new bonds with palladium. Because palladium is gaining groups here, the number of electrons will increase, but simply, the metal is being oxidized and groups are being added. Reductive elimination is next, and it is kind of like the reverse of oxidative addition. Here, what is happening is two groups are being removed or eliminated from nickel or metal in this example, and they are going to form bonds with each other. So we are going from 16 electrons to 14 here because the nickel is losing two groups it was attached to. This reaction is called reductive elimination because our metal is being reduced and groups that were attached to the metal are being eliminated. Now we have ligand insertion, which I forgot to draw half of. Luckily, the book has a great example of this, so we can work with what we have here. Ligand insertion is kind of like oxidative addition because both involve the insertion of a new ligand. However, here, instead of a metal coming between an existing bond, we have an L ligand coming between a metal and an R group of some sort. This is going to be a syn addition, so groups are going to be added to the same side of the bond. With this reaction, there are two sub-reactions. We have a 1-1 insertion, where a new bond is formed at the same atom that was bound directly to the metal. So what we see here is the methyl group that it is holding onto. So what we see here is that methyl group that is holding on to its bonding electrons is coming off the metal, then moving over to the bond with the carbon that is already making its way towards the metal. So if I'm showing that here, this is going to be coming off, and it's just moving over right over here. It's just moving over one space right here, essentially. What's different here is the bottom example here is going to be a 1-2 insertion. It's a little bit less common. So the group moving will move to the atom adjacent to the group already bound to the metal. So as we see in the reaction on the screen, that arrow group is coming off and joining the group that is inserting itself at the end. So what we're doing here is we're taking this guy, and instead of coming to, something like right here, like with that 1-1 insertion, it's going to be making its way over to the end of what was just added. So this was just added here. This is coming to the end of it instead of coming, say, right here, which is what a 1-1 addition would look like. Lastly, we have beta elimination, and again, I apologize, we are working with another example directly from the book. So what we are looking at here is another elimination reaction where a group is leaving a metal ion of some sort, but hydrogen is coming to take its place essentially. So we have the beta hydrogen shown in pink. The reason it is a beta hydrogen is because it is 2 carbons away from the metal. So this would be if there's a hydrogen here, like these 2 that are here, these are alpha hydrogens, and then because this is 1 more carbon removed, it's going to be a beta hydrogen. So what happens is this hydrogen is coming in to balance out the palladium as the R group leaves, so this whole thing right here being that R group, let's circle that, this whole guy is going to leave, and this hydrogen is going to come in and kind of balance things out with that palladium. It is not bringing electrons with it though. Those are used to form a double bond to balance out that leaving group. During this part of the mechanism, the number of electrons are staying the same. Then the leaving group, right over here, dissociate, like it says right here, which causes an increase in the number of electrons to 16, which as we mentioned before is more stable. Again, 16 and 18 electron rules. These reactions will be syn addition reactions. So finally, let's look at applications of these fundamental reactions. First, we have the Heck reaction, where an alkene is going to be coupled to an aryl bromide or iodide with a palladium catalyst. So here you're going to see a syn insertion of a nucleophile, which, as seen above, is styrene, then syn beta elimination of the halide group. Essentially, this is like a ligand substitution. What you can see is this guy here and this guy here are going to come together to form this right here. And that is going to be a syn beta elimination, then a ligand substitution. Next, what we have is the Suzuki reaction, or Suzuki coupling as it's also called. This process is going to use an aryl or phenolic boronic acid with an aryl or phenolic iodide or bromide. You're going to see substitution where the boronic acid, this guy right here, is going to be removed and a group will be added in its place. So it's going to be added right about here, and then reductive elimination will occur and 2 groups will leave, forming a new compound on their own, but we are obviously going to be focused on this guy as our product right here. That is a combination of those 2 starting materials. Next, we have a still reaction. First, we have transmetallation, or the switching of ligands between our starting materials. Then, which we have metals here. So again, switching there, transmetallation. Then reductive elimination, where the 2 groups are removed and form a new compound on their own. Then oxidative addition, where those 2 new ligands from a pre-existing bond will attach to the metal to form our product right here. Lastly, we have organocuprate reagent reactions. Here we have nucleophilic dissociation, where the iodide here is going to dissociate after the addition of this lithium divinyl cuprate right at this carbon here. Sorry, it's getting a little crowded. And at the end, it's going to form a styrene because of a new CC bond forming. Not just a styrene, of course, but at the end of the day here, we are forming a new CC bond, and that's what's important to take out of this one. Hopefully this was helpful, and hopefully you can use it to go back and reference the book as well.